Well, welcome everyone. I'm Alison from the Postgrad Association. Here we are, part two of intermediate statistics and SPSS with Megan Lee today. So just a couple of reminders before we get started that next Thursday is a public holiday. So part three, which will be advanced statistics with Megan, will be on the 2nd of May, like the Thursday after. We won't be here on next Thursday. It's Anzac Day. I'll post a couple of links into the chat to become a member of the Postgrad Association, and also where the recordings go up on our YouTube. So thanks everyone for your attendance, and over to you, Megan. Thanks.
Thank you, Alison. Firstly, I'd like to apologize for not having a video. My Bond laptop, for some reason, it's not working like that. So that's my first apology. The second thing that I would like to share with you all, and I do this every time I present for the Southern Cross Postgraduate Association, is to make a big shout out to the association. I was a member of the Southern Cross Postgraduate Association during my PhD, which I finished in June of 2022. And I had a bit of a rough patch during my PhD, and the members of the association, plus all of the people that I met networking with the association, really helped pull me through. And I don't think I would have finished my PhD if it wasn't for the support that I received from the association. So if you haven't already, I would highly recommend joining and getting involved in like the Praxis conference and getting to know your peers. Higher degree of education can be really lonely at times, and the association is there just to pull everyone together so you don't feel like you're the only one experiencing some of the difficulties of higher education, I guess. So I know I say that every time. A little bit of information about me. I have been working at Bond University for about 3 years now, but before that I was a teacher and a student at Southern Cross. I have expertise in statistics, research methods, both qualitative and quantitative. I'm a bit of a mixed methods researcher. I don't believe that you can ever find the true answer to any one research question using either quantitative or qualitative alone. So that's where I sit. That's my research ethos, I guess. You can find me on my email if you want. I am welcome to any and all questions and queries and helping people with their statistics. I can also help find tutors if you are in need of something like that. You can also follow my research journey at foodmooddoctor.org or on my social medias, foodmooddoctor. So, Alison, do you have anything else that you want to cover before we get into what we're doing today?
I'm all good. Happy to get going.
Excellent. So what I might do then, we've got about 10 people here today. I just want to know how many of you attended or have watched the recording for the beginners statistics and SPSS class that we did last week. So just feel free to type into the chat box or put your hand up in the emojis. No one? That's okay. Helen was here. Excellent. Nice to see you again. Leah wasn't. Okay. So Massim was here. I do remember seeing you, Massim. Marisha was here. Oh, excellent. So most people who were here last week are back. That's good to see, for starters. And those of you who are attending just today, please don't feel like you're missing out on anything. Last week in the beginners workshop, we basically covered taking the information out of a survey like Qualtrics or SurveyMonkey and uploading it into SPSS for data cleaning. And then we went through cleaning a continuous variable, cleaning a categorical variable, and how to get your data set up for analysis. So we didn't actually move on into any of the data analysis in last week's workshop. That's what we're doing today. So the intermediate statistics and SPSS workshop is where we're moving on into focusing in on kind of the first steps that we take in any data analysis. And please be aware that it is an important system that we follow, and we don't go out of the system or out of the order. So the first step is that data cleaning. So if you would like more information on how to do that, feel free to watch the recording. Alison's popped that up into the chat box there. And today we will move on into a little bit more about the analysis side of things. So what I want to get to know from you is, in the chat box, if you can write in what degree you're doing, what your topic is, if you are doing a honours psychology project or a PhD or a Masters of Research, and what level from 0 being no expertise with SPSS and statistics up to 10 being an expert at SPSS and statistics, what kind of level you feel you might be at with statistics, just so I can get a gauge of what sort of level I should be pitching at today. Honours psychology in a 4, that's good. And 4 is about where we usually are around psychology honours. We're very, very lucky in psychology that we, despite getting a psychology degree and having all this wonderful information about the brain and how people work, at the end of your degree, you also have by far the most advanced statistics knowledge out of any degree that you can undertake. And so a lot of psychology students actually can go out into the world after their degree and get a job in industry and statistics in any type of industry. So it kind of opens up the world to psychology students. Even if you don't choose a degree or a career in psychology, there's so many other careers out there where your statistics knowledge will be valuable, which I found after I finished my PhD as well. PhD business and a 4, PhD a bit rusty on stats 4, that's okay. Honours psychology 3 to 4, PhD in health science 3 to 4, PhD for me also and a 4, marine ecology, that sounds interesting, and a 5, environmental science, PhD and a 4. So everybody's kind of around that kind of intermediate level anyway. So that's really good. I think also the next 2 workshops on the 2nd and the 9th of May will also be useful, where we move into a bit more advanced statistical analyses like regression and ANOVAs, whereas today we're going to do the 2 easiest analyses, being correlations and t-tests. Excellent. So everyone's kind of on the same page, around about the same level, which is great. All right. So today we will be...
Alison from the Postgraduate Association. We're very pleased.
Today we will be looking at what's known as descriptive statistics. Now, I'll get into the definition of descriptive statistics and inferential statistics in a moment, but descriptive statistics are basically the statistics that we use to look at what our data looks like. If we have 50 participants, what do they look like? What is their average age? How many are men? How many are women? What kind of income does everybody have? Are they religious or non-religious? What sort of, what does our data look like? And then our inferential statistics basically answer the research question that we have. Now, we started with some research questions last week, and we will continue with the same sort of topic. And then for the second half of the workshop, we will move into using SPSS and all the tips and tricks that I have there for data analysis. So let's start with understanding your knowledge of descriptive statistics and inferential statistics. So who can tell me a definition for what descriptive statistics are? Feel free to type into the chat box, what are descriptive statistics? What is the definition?
I'll have a crack at it.
Yeah.
Good morning.
Hi, Daniel. Nice to see you again.
And you, Megan. Well, essentially, descriptive statistics describe the sample that you actually have using descriptors such as medium and mode and measures of central tendency. So they're describing the sample, whereas inferential statistics make inferences about what might be the case in larger populations given the sample that you have.
Very good. That's a perfect explanation of descriptive statistics and inferential statistics. Backed up by Miranda, Katerina also said describing the data, summary statistics for your sample. Excellent. So descriptive statistics are always our first stop. We want to see what our participants look like or what our data looks like. So as Daniel also said, inferential statistics are a tiny little bit different. So inferential statistics are where we start to answer our burning research questions, where we make inferences about the small sample that we collected and whether or not they would generalize out to a larger population. So one of the things with statistics is that it is improbable, if not impossible, to collect data from the entire population from which you're interested. And I always use the example of university students because it's what we know. All the university students that are in the world right now attending university, that's our population of university students. If we want to know something about university students, we can take a sample from the university that we are working at or studying at, and we can make inferences that these university students may have the same characteristics and therefore represent the entire population of university students across the world. Now, this might be a little bit misguided because individual differences of all people are different races, people are different genders. If you had a whole group of students who were high distinction students in one class, and you sampled them, that wouldn't then infer out to the general population. So we have to be very, very careful with the samples that we collect to make sure that we can generalize out to the larger population. But all in all, that's what our inferential statistics do. Our descriptive statistics tell us what those university students look like in our sample, what their ages are, how similar they might be to a general population of university students. And then the inferential statistics tell us or answer the research question that we have about that population. Good. Now, Daniel also mentioned the types of descriptive statistics that we can find. Now, the most common is our mean. What is our mean? If you can, type into the chat box and define what is a mean. Miranda, the average. Yeah, exactly. And how do we find an average? Add them all together, then divide by the total number. Exactly. So age is a really good example of finding an average. If we took all of our university's students in our sample and we found out what everybody's age was, and then we added all the ages together and divided by the number of participants that we had in our sample, then we could find out what the average age of the participants or the university students are. And then we could see if that age was similar to or different from what the general population of university students is. Now, an interesting thing about the average age of Southern Cross University students, can anyone tell me there might be a little bit of a strange anomaly with SCU students compared to the general population of university students in Australia? Anyone willing to hazard a guess? Right, Alison. So the age average is a lot higher than the population of university students, particularly in Australia. So we have much more mature age students. Daniel's got an exclamation mark. Maybe the classes that you teach, you have younger students, Daniel. But overall, SCU does have a higher average age. Whereas Bond University, where I work, we have mostly school leavers. So we have a lower average age than the normal university population in Australia, which is very, very interesting. We have very few mature age students at our university. So that's a really good example of a mean. Now, can someone give me a definition of what a median is? Is it because of online students? It is, but it's also the regional component of SCU. Lismore, Coffs Harbour campuses, even particularly the Gold Coast being also down the southern end of the Gold Coast being part of the regional area. It's a really good framework for people who are mature age or have children to be able to attend university compared to some of the more city ones. And I think they also recruit particularly to mature age students as well. I think it's on purpose. But we could look into that. We could do a research project and find out. Has anyone got me the definition of a median? The median is the middle. Yes. The number that is in the center of the line of numbers in order. Yeah. So if we took all the ages of our university students and our youngest was 18 and our oldest was 75, and we cut them in half and we found out who the very middle age was, let's say 35, that's the median. Now, why would the median be a more useful would be more useful than an average? When would we use a median rather than an average? So age is actually a really good indicator of this. So after what we said, the average, it gives an idea of how high and low it goes. That's right. So with our average age, say most SCU students are mature age students around the age of 35 to 40. And we look at our data set where we've got an 18-year-old who is the youngest, and then we have very many students who are kind of around that 35 to 40 age group, and then our 75-year-old. If we take the average of all of those, and we can usually, the average is usually skewed maybe by that really young person, maybe by that really elderly person. So using the median, it kind of cuts those outliers off the ends and shows us what the middle number is. Now, you'll quite often see the median reported in housing prices in Australia. So we very rarely hear the average house price in Australia. We usually hear the reporting of a median. And the reason for this is because there are very many people who own homes around, say, the 750,000 mark at the moment. I'm using data from my hometown in Mooloolaba, so that's what the median is usually there. There are some people in Mooloolaba, though, who own million-dollar mansions, but there's not very many of them. Most of us, our houses are worth $750,000 to, say, $900,000. So those people at the higher end really skew that average. So that is why the median is most commonly reported, because it is it's the best indicator of what the housing price is in a current area. Now, what about the mode? What is the definition for a mode? The most often occurring number. Yep, good. So if we take age again and we have the most number of 35-year-olds in the data set, that would be our mode. We use mean, median, and mode for different types of variables. And as you saw before, the median is much better for certain data, whereas the mean is better for other data. So this is why we have our 3 different measures of central tendency, each being useful for its own thing. And you will know that once you get into the data later on. Now, it is important to know kind of our averages and our middle numbers, but them by themselves don't really give us that much information. So what we need to pair those measures of central tendency with are our measures of dispersion, or how far our data is from those measures of central tendency. So using age of university students again, if our average age is 35, our median is also 35, and our most common score is 35, that gives us a pretty good indication of what our data looks like. And it also tells us that our data will be normally distributed. If the median, the mode, and the average are all the same number, it's a pretty good indication of a normal distribution. And we're going to go into normality in a second as well when we go into assumptions testing. But what it doesn't tell us is what everybody else in the data set kind of looks like. So if we compare our average with a measure of dispersion like the range or the standard deviation, then we know a little bit more about what our data looks like. So who can tell me what the definition of the range is? The spread of the data. Good. And how would we find the range? Right. So we subtract the lowest number from the highest number. So in our case where we have our 18-year-old and our 75-year-old university student, and most of our university students are around 35 to 40, if we take 18 from 75, we get 57, I hope. And then 57 becomes our range. But the range is not the most accurate measurement of dispersion, because our 75-year-old and our 18-year-old might be massive outliers compared to the 35 and 40-year-olds that we have in our data set. So it's not giving us a really good indication of what that range is. And this is why the standard deviation is the most commonly used measure of dispersion, and it pairs really well with the average. So a standard deviation is, on average, how far all the participants are from the mean. So I know that can be a little bit confusing because the word average is in that sentence twice, but it is, on average, how far our participants are from that mean. So how far on average, each of our participants are. If the standard deviation is small in relation to the mean, then we have a very tight dispersion and there's not much range in ages, which is a good thing. So our standard deviation is nice and small, and it tells us that there's not much range in age groups. So if our standard deviation was 2 in this case, and our average was 35 years old, then most of our participants would range between 33 and 37. But if our standard deviation is 20, then most of our participants would fall somewhere between 15 and 55. So you can see there would be a much wider range of ages in that data set compared to a standard deviation of 2. Is everyone happy with the definitions of range and standard deviation before we move on? All good. Perfect. Right. The next thing that we need to know before we jump into our data set and before we start analyzing data is, how do I know what test I need to use? Now, I'm going to show you two tables in a moment, one on how to select the appropriate test for continuous data, and the other on how to select the appropriate test for categorical data. But before I do that, I just wanted to share with you this stats flowchart. It is a website completely free, and I'm going to pop it into the chat box as well. It is a flowchart where you can put in what types of variables that you have, how many dependent or outcome variables, how many independent variables or predictor variables. Yes, Katerina, we will give you the slides after this as well, and link to the recording. So the stats flowchart, you put in all your information about what variables you have, and it will spit out at the end what data analysis test you should use. And I find it really helpful, particularly if you've got lots of different levels of your independent variable or your predictor variable, or if you've got a mixture of continuous and categorical variables. So before we get into these tables, a quick refresher from last week, because none of this will make sense without this. Could you please define what a categorical variable is? Any variable that can be put into categories. Perfect. Likert scales, nominal or ordinal. So our nominal categorical variables are any that can be put into categories that don't have an order, and our ordinal categorical variables are any categories that have an order, like where you finish in a race. Good. Perfect. What about our continuous variables? What are they? What do they mean? What is a continuous variable? Ratio, yeah. Relies on a continuum. Think of the ladder or lying on a ruler. Perfect, Miranda. Thank you. Negative infinity through 0 to positive infinity. I can tell you were listening very well last week. Excellent. So a continuous variable is any variable that can lie on a continuum from negative infinity through to 0 in the middle to positive infinity. Great. They are commonly called our ratio and our interval data, with ratio having a perfect 0, which means at 0, there is an absence of that variable. So height is a ratio variable. At 0 height, there is no height. Whereas temperature is an interval variable. After 0, there still is temperature. It's just negative temperature. So there are continuous and our categorical variables. Last test. What is an independent variable? Define an independent variable. The variable that is manipulated. Excellent. Good, Katerina and Miranda. The independent variable is the variable that is manipulated in an experiment. The predictor variable is also called the independent variable, but it is a predictor when it's in a survey or in a experiment where you do not manipulate the variable yourself. You don't have control over manipulating the variable. So usually in surveys, we call our independent variable the predictor. Who can tell me what the definition of the dependent variable is? The outcome, exactly. So the dependent variable is the variable that we see the outcome in an experiment, and it is also called the outcome in surveys. So if you're doing an experiment, you would have an independent variable, which is the variable that's manipulated, and the dependent variable, which is the outcome. And in surveys, you would have your predictor and your outcome variable. Excellent. So these are all very important definitions. And the reason that I tested them on you is because you need to understand them fully to understand what is going to be happening in your statistics when you get into SPSS. Now, the two different statistical tests that we look at today will be relationships and predictions using correlations. And you can only do correlations on continuous data, or when your dependent variable is continuous. Whereas group differences are using t-tests are more along the lines of when you have experimental data or you have two groups that you want to see a difference in, or the difference in the averages. So let's just have a look really quickly at the group differences for with a categorical predictor. So when your predictor or your independent variable is categorical, you would be looking at differences between groups or the differences in the averages between two groups. When your outcome variable or your dependent variable is categorical and your independent variable or your predictor variable is categorical, you would do a non-parametric test called a chi-square. If your outcome variable is continuous and your predictor variable or your independent variable is categorical with two levels, say male and female, and the two groups that you're testing have the same participants in each group, so male and female won't work with this one, it will only work with an independent. So let's have a think. I will think of an example. So let's say diet and depression. Say we take a group of participants and we measure their depression levels. Then we give them a healthy diet, and then we measure their depression levels again after having the healthy diet for, say, 6 weeks. Then we would run what's called a paired t-test. Our outcome variable for depression, so the depression score is continuous, lies on a continuum. And then we have a categorical predictor, which is 2 levels before and after the healthy diet. And in those 2 levels, the participants are the same. So the participants in the before group and the participants in the after group are the same participants. That's when you would use a paired t-test. Now we're going to talk about assumptions testing in a second, which are things that need to be completed before we can do any type of analysis. If our assumptions are not met, then we would use a non-parametric test called a Wilcoxon signed rank test. Now, my second example is if the same thing, if we have a dietary pattern and depression research question, and we take 2 groups of participants with different participants, and we give them both a healthy diet, and then we measure their depression symptoms, and the participants in both of the groups are different participants, so we don't have to do before and after now. We're just measuring 2 groups, one with a healthy diet, one with an unhealthy diet, and measure their depression at the end. Then we are doing an independent t-test where our dependent variable or our outcome variable is still depression measured on a scale, and our predictor variable or our independent variable is the 2 different groups. And each of the groups, one is healthy diet, one is unhealthy diet, have different participants in each. Then we would run an independent t-test. So we're going to look at t-tests today. If our assumptions aren't met, if our data is not normal or not linear, or there's something wrong with the sample size, then we would use a Mann-Whitney-U test. If you've got more than 2 levels of a categorical variable, then you would use an ANOVA. And you can do ANOVAs with groups with the same participants or groups with different participants as well. And we will move into ANOVAs when we go into our more advanced statistics workshops in the coming weeks. Does anyone have any questions about group differences or t-tests before we move on?
This might be a silly question, but I'm wondering about the giving the score of depression. If it was on, well, so you said it was on a continuous scale, but if you had it to where it was just basically a rating,
Yep.
That would be more categorical because is that correct?
Yeah. So
Yeah,
the way
okay.
that we measure depression scales normally in surveys is we give participants, like, say, 20 questions on a Likert scale, which is categorical, from strongly agree to strongly disagree. This is how I've been feeling in the last week. And the participant answers the 20 categorical questions. And at the end of that, we then, and if you go back and watch the recording from last week, we take those categorical questions and we turn them into a continuous score by adding all of the questions together of the 20 that they've answered. And then that makes it a continuous variable. But you can, say, take the depression scores, because depression always has a cutoff score, right? Particularly for the scale that we're using today, the Center of Epidemiological Studies of Depression scale, it has a cutoff score of 16. So any person who's over 16 would be classified as having diagnosable depressive symptoms. Anyone under 16, the cutoff score of 16, would be classified as not having diagnosable depressive symptoms. So you can then use that information to create a dichotomized dependent variable with two categories, and then you could run a completely different analysis on it. So it's completely up to you. And it's really important that you make these decisions about your data before you start data cleaning and data analysis. And this is why we have pre-registration in Open Science's framework, so that all researchers are saying, well, this is the analysis I'm going to do before they get into it, so that they don't get into the data and then try and do different things to get the result that they wanted, basically. Excellent question, Miranda. Katarina, you have your hand up.
Yes, I might be like, I don't know if you want to answer actually this question now, or is it better to wait, but if I have got 3 groups of continuous variable, for example, and 2 levels of categorical, will it be still ANOVA, and will it be between and within groups design, or
Good question.
yeah?
Let's have a look and see if I can figure this out. So, and this is why that stats flowchart link that I put up is really important, because once you start having 3 dependent variables and 2 predictor variables, and some groups have participants all in the same groups, some groups have different participants in groups, it becomes a complete nightmare. But that statistical flowchart will tell you exactly what to do. It sounds like ANOVA. How many outcome variables do you have?
I have got 2.
What are
Amount
they?
and variety of pleasure. Amount and variety of pleasure. So, oh, sorry, outcome. It's I'm measuring people who have symptoms of anhedonia. I will divide this all people on 3 groups, like low, medium, and high symptoms of anhedonia, and I will
Yep.
measure how much, what amount and variety of pleasure they experience. So, yeah.
Yeah. Yeah. You need to do the stats flowchart. I could work it out if I had time, and like I could draw myself a little map, and that's what I do. I do like a mind map of all of the variables, whether they're continuous or categorical, and how many categories that they have. And then once it's on paper in the little mind map, it's easier to figure out what stats to use. But yeah, it can get quite tricky. And by the time we do the 2 advanced statistics workshops, we should have that worked out, right? So yeah, okay, so that is when we have categorical predictors. When we have continuous variables and we're looking at relationships rather than group differences, our analyses are different again, right? So if we've got continuous outcome variable, a continuous predictor variable, then we're always doing Pearson's R. Pearson's R is the easiest statistical analysis of all time. It's my favorite. It's the one we're doing today. However, if our assumptions aren't met, you can also do a Spearman's. Or if you've got categorical data, we can go down a whole rabbit hole of Spearman's as well. That's one of the ones we're going to do today. And then when you're getting a little bit more advanced and you're wanting to know with your two continuous variables, whether or not there's a relationship, that's what our correlation will tell us. If we want to predict from those relationships, then we move into our regression. So our simple linear regression, our multiple linear regression, and then, as Miranda said, if we want to dichotomize or categorize our dependent variable into two, we can also do what's known as logistic regression, and we will do that in our final week. It all sounds a bit scary, but to be honest, it's really not once you step through it in simple language. So that's a little bit of a touch on what we will look at. But keep in mind that to do correlations, you should really have two continuous variables. And when you're looking at differences between groups, you want to have a categorical predictor or independent variable. Good. Any questions on that before we move on? Because we're going to get into the data very shortly.
Could you pop that slide, the two back up again? Yeah, the
That
previous. No, the previous one to that.
That one?
Yes,
Right.
this. Thank you. This is where I'm trying to get my head around this stuff effectively. That's great. That's fine.
And just keep in mind that within design means that both groups have the same participants in them. And between design means that both the groups have different participants in them. So your within design is usually like your before and after type style experiment or survey. And your between design is when you have like an intervention and a control, or two groups that are having different interventions. Yes, Daniel.
Yeah, thanks, Megan. Practically, when does one say the groups are different? As probably most of us would know, you start with a pre-post arrangement, and you know, perhaps 10 people in the pre, and then for some reason one or two of those people might be different people or might drop out. So the groups are no longer paired. So at what point do you say, oh, they're not paired anymore?
Yep. So that's a really good question. And it really depends on the research design. We do a lot of t-tests and independent paired t-tests in longitudinal study designs where thousands of people will drop out. It doesn't affect your results as much as you think. As long as your assumptions testing, which is what we're about to segue into, thank you, Daniel, are met, then you don't really have to worry about your two samples being identical. However, when we're doing paired samples t-tests, if one of your participants drops out, then you've lost both points of data, really, haven't you? So that can be a problem. Which is why we always go to G-Power, make sure that we've met those sample sizes and go beyond our sample size so that we can account for attrition. Good question, Daniel. Right, so let's talk about assumptions testing. This is the final thing that we need to ensure before we get into our data analysis. And I know I've been talking for the last 45 minutes without actually being in the data, but all these things need to be nice and firm in your mind before you go into your data. You need to know all of this. So assumptions testing. If we move on into our data analysis without ensuring that our assumptions are met, then our results can be faulty or wrong. So assumptions are super important to ensure that they have been met. The most common assumptions are the assumption of independence, the assumption of linearity, and the assumption of normality. Independence is met in the study design. So we don't actually have to do any specific checking of independence, as long as you have made sure that in your experiments or in your surveys that your participants have not influenced each other's answers, then independence should be met. And that one person hasn't done the intervention and the control group, or one person hasn't done the survey multiple times, because that would influence independence, because those answers are not independent of each other. So as long as you can ensure that in your study design, then independence will always be met. That's our first assumption. Our second assumption that we must ensure before we can analyze data is linearity. Linearity means that our data falls on a straight line. Now we need to measure linearity inside our analysis. So we will have a look at that, and I'll show you how to do that in a moment. And finally, and probably most importantly, is normality. We need to kind of ensure that our data fits on that normal distribution. And you'll see that bell-shaped curve, with most participants in the middle. 60% of our participants should be about 1 standard deviation from the average. So when we consider our example before about university students' age, if our average is 35 and we have 2 standard deviations, or our standard deviation is 2, 1 standard deviation from the mean is 33, another standard deviation from the mean is 37, then 60% of our participants should fall within that. And then only a very few amount, about 20% on each side, should vary from that. So we really want to make sure that our data is looking normal before we can test it, or before we can analyze it. If not, there are some things that we need to do. Otherwise, our results will be faulty. Right. So what we might do is, last week we exported the data from Qualtrics and Excel into SPSS. This week we're going to begin the steps of analyzing the descriptive statistics and exploring the data. The data set that we're using is a live data set that I collected last year in March on Vegetarians for Life. So the current data that I've been working on for the last few years has been on plant-based diet and mental health. And I've been exploring this question about why vegetarians and vegans seem to have a higher rate of depression than the general population, despite the fact that the foods that they eat are protective against depression, which is data that I found in my PhD. And one of the problems that we kept coming up with was, every time we did like a cross-sectional survey, we could only really tell whether or not the vegans or vegetarians, how they were feeling at that point in time. We didn't know if things had changed the week before or whether things would change in the future. And this is kind of a limitation of cross-sectional research, right? And another thing that we found, which was quite interesting, was when we looked at the food frequency questionnaires that we were getting the vegans and vegetarians to fulfill, a lot of them were ticking yes to some of the meat consumption questions. And this led us to believe that potentially we're not really measuring vegan and vegetarian depression and diet, but we seem to be measuring low meat consumers. Now, to get over this limitation, I wanted to look at people who were purely vegetarians and vegans to see if what we were finding in the other research was the same or different. And to get over this limitation, me and my friend Gurmeet, who is also at SCU, decided to recruit from populations who have never eaten meat. So people who've been vegetarian for life for religious or cultural upbringing reasons. So people who were in religions that don't eat meat, Hare Krishnas, Hindu, I believe, Seventh-day Adventist. And we also got people from the general population who have been vegetarian for their entire life. And this removed the limitation that some people were actually eating meat. Nobody in this survey clicked on the meat consumption questions. So that's the data set we're going to be looking at today. We're going to be looking at two research questions that we looked at last week. The first is there a relationship between the diet quality, so low diet quality versus high diet quality, and depressive symptoms in those who have eaten a plant-based diet their entire life? And the second research question is, do the vegans or the vegetarians in the data set have higher rates of depressive symptoms? Before we move on to data analysis, we usually hypothesize. So what do we think our hypothesis is for that first research question? Is there a relationship between low and high diet quality and depressive symptoms in those who eat a plant-based diet? What do we think? We must always hypothesize before we analyze and pre-register our hypotheses so we don't change our hypotheses after we've done our data analysis. Type into the chat box, what do we think that hypotheses would be? What do we think is going to happen in that first research question? There is a relationship between diet quality and depressive symptoms. Good. Our non-directional hypothesis. There will be a relationship between diet quality and depressive symptoms in those who have a plant-based diet. Thank you. You don't have to have a direction. No, I prefer a non-directional hypothesis because it means that we are measuring both ends of the question, the negative and the positive ends, and that's how I like to analyze data. What about our second question? Do vegans or vegetarians have higher rates of depressive symptoms? What do we hypothesize? There are differences in the rates of depressive symptoms between vegans and vegetarians would be our non-directional hypothesis. Good. Okay. Perfect. So what we're going to do is we're going to have a 5-minute break or a 7-minute break up to 10:30, and then we will get into the data analysis into SPSS. That's right, Matt. So the non-directional hypothesis is there is a difference between vegan and vegetarian depressive symptoms, or the rates of depressive symptoms in vegans and vegetarians, if we want to know that. So perfect. Excellent. So just a thumbs up from everyone when you're back so that I know that everybody is back from getting their coffees. Great. So what I'm going to do is I'm going to flick through the slides really quickly of what we're about to do, and then I'm going to change over to the SPSS platform. So first we'll have a look. Last week we cleaned some data. We cleaned one continuous variable, one categorical variable. I showed you how to transform a variable, and we did a little bit on how to create a total score, as I explained to you all earlier, from 20 Likert questions on the depression scale, how we turn that into a total score. So we'll have a look at the full data set in its clean state. Then we will move on to descriptive statistics, which should always be the first step before you move on to analyzing your data to answer your research question. We will look at categorical variable descriptives like gender, geographical location, marital status, and education. Then we will look at our continuous variables, so the descriptive statistics of what our data set looks like for age and BMI, depression scores, and diet, which is part of the variables of our question. Then we will talk about our assumptions. Has independence been met? whether or not normality has been met, and linearity. So we'll go through that in the data set, and we will produce the graphs, and I'll show you how to produce the graphs to ensure that your data set is ready for analysis, and what to do if some of your variables do not meet those assumptions. Then we will step through correlation, the easiest analysis of all time. It's the little brother, it's the best one, it's the easiest to run, it's the easiest to interpret. And that will be to analyze a research question about the relationship between two continuous variables. And then finally, we will talk about differences between groups. So our t-tests. So we're looking at when our predictor variable is categorical and our outcome variable is continuous. And just for fun, there is one extra assumption that comes along with group differences, and that's our assumption of homoscedasticity or heteroscedasticity. What that means is that when you have two groups with the same or different participants, the groups need to have variances that are kind of equal before we can move on to our analysis. Because if our groups are very different, as Daniel was saying earlier, if they're very different, we don't meet that assumption, and we need to apply a transformation. Now, luckily, SPSS does the transformation for us automatically in our analysis. So it's not a big deal. It's just something that you need to be aware of. And that's it. That's what we're going to do. So I'm now going to unshare my PowerPoint. And I'm going to share my SPSS data set. So please tell me if you can see that when it pops up. Okay, perfect. Good, good. Now, this is the variable view in SPSS, which shows us all of our different variables. So the variable tab here, the name of the variable. So an example is gender, what type of variable it is. They all should be numeric. SPSS does not like words. It won't analyze words. So making sure that that column is always numeric. I always have my column and my widths at 8. And that just means that all of these in your data view will be even and consistent. Then we've got how many decimal places. Now, none of my variables require decimal places apart from body mass index. So they are all set to 0, but that will depend on your variables. And then we have the label. The label in this column is what will come up on your figures and your tables in SPSS to put into your publications or into your assessments. So keep that in mind when you're labeling each of your variables. The values box is for categorical variables, where we tell SPSS what our variable categories are. So for gender, we've got male valued at 1, female at 2, transgender at 3, non-binary at 4, and 5 was prefer not to answer. We don't need to worry about the missing column, as it is a hangover from SPSS days of old. So we don't really worry about that because SPSS adjusts for missing data now. I center align everything, which just means all of these numbers will be in the center of the box. And then the most important column of all is our measure. So we're making sure that our variable has the correct measure nominated to it. So nominal is our categories, and you'll see here our green, our red, and our blue category for gender. Then we have age, which is our continuous variable. And you'll see here scale is the nomination for our continuous variables. And it has a little ruler next to it. Then we have our ordinal variables, which are variables that are categorical but in order. And you'll see a little bar graph next to that. So just ensuring that all of the measures of your variables are correct before you analyze is very, very important. Now, this is all being completely cleaned. And then in our data view tab, we have each participant is a row And each of the questions that the participants were asked is a column. So gender here are nominated ones and twos. If you would prefer to see the word categories, you click on this button up here, which is A to 1, and it will tell us what our values are instead of what number we coded the categories as. I find that is easier when I'm analyzing data, so I would keep my data set always in words instead of numbers, but you can change it back to and from with that button. So we can see here that our first participant is a male who is 29 years old. He has a BMI of 22.13, so that's around normal, I would say. Usually I have a BMI category, but I haven't done that here so that I can instantly see what category of BMI that's in, but I'm pretty sure that's normal. He lives in Australasia, so somewhere in Australia, New Zealand, or the Pacific. He's married. He has a postgraduate level of education. He is vegan, and he's self-nominated as vegan. He gets more than, I have to extend it out, more than 3 hours worth of sunlight exposure a week. And he has a depression total score of 10. Now, keeping in mind the depression total score ranges between 0 and 60, and anyone under 16 is classified as not having depressive symptoms. So he's under that cutoff score, and I've categorized that here. So he has no depressive symptoms. Now, you'll see here that the top 21 participants are all under that cutoff. So that's interesting to start off with without even analyzing our data. That's kind of telling us something about our data set. They seem to be very low in people who have symptoms of depression. The next column is our dietary screening tool total. It ranges from 1 to 105, with higher scores meaning better diet quality. So 78 is pretty high compared to the rest of what we've got in this column. So he's got pretty good diet quality. So we can see a little snapshot of participant 1 there. So we have currently got over 300 participants, but when we were data cleaning last week, we had over 400, I believe. So we lost a few participants in the data cleaning stages. We made a decision as a research team before we even started collecting data that we would eliminate any participants who didn't answer all of the depression totals, all of the depression questions and all of the diet questions, because they're our dependent or our outcome variable is depression, and our independent variable or our predictor is diet. So any participant that didn't answer those 2 questions, we a priori, before we collected data, we decided we would eliminate. But your team will make those decisions together. Some people will not eliminate that many people, some, and it depends on your research question. Right. So the first thing that we do when we have our data set nice and clean in this way is to look at our descriptive statistics. What does our data set look like? We got a little snapshot of participant 1 there, but what overall does our data set look like? In particular, we're looking at those descriptive statistics or those central tendency, the measures of central tendency first. So let's first look at our categorical variables. So to do so, we would go to Analyze, Descriptive Statistics, Frequencies, and then we would put our categorical variables into the variable box of variables that we're interested in looking at. So we've got gender, geographical location, marital status, education level, whether they're vegan or vegetarian, what types of vegan or vegetarian that they are, how much sunlight exposure that they received. They're our basic demographic questions. We want to keep our display frequency tables box checked for our categorical variables. You can also click this box that says create APA style tables, and it will only include in the tables the important data for APA 7. And then for categorical variables, we want to click on charts, and we would like SPSS to provide us with some bar charts with percentages, because figures are much easier to interpret than tables. So let's go and have a look at what we found. Now we wait a moment for SPSS because it takes a little while. You'll see down the bottom here where it says running frequencies. That tells you that it's still thinking. And once it is finished thinking, an output window will pop up. But SPSS traditionally is quite slow. So we'll wait a moment. Can everyone see the output pane, or do I need to stop share and reshare the output window? Can you still see the stop and reshare? I thought that might be the case. Right. Okay, now can we see our output? Perfect. All right. So this is what SPSS will spit out to you for your categorical variables. So the first box tells you how many participants you have who have answered each of those questions and how many were missing. Not that important for demographic variables when you're providing your descriptive statistics. Keeping in mind, with these statistics, you'll usually produce a participant characteristics table, which is usually table 1 in your publication or in your assessment or in your PhD chapter. So our frequency table here, it tells us how many males do we have in our data set. Anyone want to hazard a guess how many males we've got in our data set? 115. And how much of a percentage of males do we have? 36.1. Keep in mind, when you are reporting statistics, percentages are always reported as a whole number. So that would be 36% with an N of 115, which means we've got 199 females, which is about 62% of our data set. That's pretty good when it comes to this type of data. Usually we have more women than men, but 115 men's actually really good. So then we've got our geographical locations, each of the where everyone's from, mostly from India and Australasia. So about 60% of our data sets from Australasia and India, which is just an element of the recruitment and the recruitment team. Gurmeet, my friend, and I were both recruiting. Gurmeet is Australian Indian, but has a lot of connections in India. So that is why a lot of the recruitment would have been seen by Australasians and Indians, but it did get out to the rest of the world, which is kind of cool. Through snowballing on, we got about 40% of our data set just from snowballing across the internet. So that's kind of cool and shows us a little bit about our recruitment technique and what we can use that's beneficial next time. Marital status, we've got 83% singles, 190 married. Usually with marital status, I would create a new variable, partnered and unpartnered, which gives us a bit more information than single, de facto, married, divorced, widowed, that type. That's completely up to you, how you want to display your information in your participant characteristics table. Then we've got education level, mostly postgraduate and bachelor's degree, so highly educated data set. So this is telling us a little bit about our data. Mostly female, mostly married, mostly highly educated. So we're starting to get a little bit of a picture or a snapshot of what our data is actually looking like. We've got 164 vegans, 154 vegetarians, which is excellent because we wanted to kind of keep those groups similar. So that happened during recruitment. If we were getting more vegans than vegetarians, we would push out a recruitment for vegetarians to try and keep those even. So that's important to consider if you are going to do group differences. Like Daniel said, you want to keep things kind of similar. Sunlight exposure also. But now we've got our bar charts, gives us a much easier interpretation of what our data set looks like. So our gender, our geographical location, we can definitely see there it's mostly Indian and Australians. Our marital status, mostly married, second is single. But if you clustered those into each other, partnered and unpartnered, I'd assume partnered would be higher. There's your education level, highly educated data set. Our vegans and vegetarians are very similar. And our sunlight exposure. So kind of clustering around 10 to 30 minutes and more than 3 hours. So that gives us an idea of our categorical variables. Keeping in mind, when you do your write-up for this, you would only explain the important information, just like I did then. So mostly married, mostly female, similar amount of vegans and vegetarians. Please refer to table 1 is how you would report those in text. So you don't report all the information, just the most important and the most interesting aspects of your participants. So now I'm going to reshare my data, and we're going to have a look at our continuous variables and what they look like. So analyze, descriptive statistics, frequencies. Now, SPSS does this really good thing where it remembers what you did last time. And this is quite helpful because sometimes I forget to do things and I'm like, but it's already in there, so you don't have to change anything. But in this circumstance, we want to reset the frequencies box and we want to put in our continuous variables. So we've got age, body mass index. Now, this is a contentious variable because most people suggest that BMI is not a very good indicator of health. And we don't actually ask participants what their BMI is. We ask them what their height and their weight is, and then we create a variable for BMI. We also don't usually like reporting it too much because it's not very sensitive, and it isn't great, but that's all we have at the moment in survey type research to kind of measure health. The depression score, so the Center of Epidemiological Studies of Depression score, our diet quality score, our social connection score, and our sleep quality score. We also have the DAS, anxiety, stress, and we've got physical activity as well. But the main variables of interest for us are those ones here, with our social connection and our sleep quality being our covariates of variables that may influence the outcome that aren't our predictor variable. Then we'll go up to statistics, and we want to see our central measures of central tendency like mean, median, and mode. We also want to see standard deviation. We can have a look at the range if there's a big difference between the standard deviation and the range. And I also like to see the very lowest and the very highest score. Continue. For charts, we want to see histograms. So histograms are like a bar chart for a categorical variable, but what are used when you have a continuous variable. And we want to see how close those histograms are to normality. And then that will help us not only look at our descriptive statistics, but also at our first assumption of normality. Okay. Stop share. Then I will reshare my output. Can we all see the output? Yay. All right, so this is our continuous statistics. It looks a tiny little bit different to our categorical. We've got a table in perfect APA 7, which is amazing, for averages, median, the mode, the standard deviation range, minimum and maximum scores for age, BMI, depression, diet quality, social connection, and sleep quality. Now you'll see the labels for the scales or the pre-validated scales that we've created total scores for have the name of the scale, the acronym of the scale, what the scale ranges between, so 0 and 60 for the Center of Epidemiological Studies for Depression, and that higher scores mean greater depression, and the cutoff is 16. I do this in my labels so that when I am interpreting the data below it, I don't have to go back and find the paper and remember what the cutoff score was and what the range was and things like that. So it's just something that I do when I'm cleaning my data and labeling my data that helps me at interpretation stage. So let's go and have a look. Can anyone tell me what the average age of the participants are? Thanks, Daniel. I've honed my craft over time. What's the average age? 40. Miranda says 40. Katarina says 39.57. Good. So when we are reporting our statistics, we report all of our statistics to 2 decimal places. So 39.57. But to make things even more complicated, we report all of our significance testing like p-values and our assumptions testing, which we'll get to in a second, to 3 decimal places. So you might need to look up the rules for rounding in APA 7. I know percentages are a whole number, statistics are 2 decimal places, and significance and assumptions testing is 3 decimal places. That's all right, Miranda. So the mean is 39.57. What's our standard deviation? $12.743 or 12.74. Good, excellent. So what that says is that if that age variable is normally distributed, that 60% of our data set would fall between, quick maths, 23 and 52. So that's quite a good range, actually. 23 to 52, that sounds good. Who's our youngest participant? Already I can see a problem with my data set, which is a bit scary considering that the youngest participant is 13. I don't know if we had ethical approval to have under 18s. Let me see how many of those are in the data set. That's a worry. One, two, three. There was 3 under 18s. And we did notice that when we were cleaning the data last time, didn't we? That's okay. Right. Are we still looking at the output? Because I know that looking back at the thing might have stuffed it up. All right. Who's our oldest participant? How old's our oldest participant? Our oldest participant is 85. Okay, so what does that mean the range is? 85 minus 13. What is our range? It's also reported there. 72. So as you can see, the dispersion of the range is highly skewed by the very young participant and the very older participant. And the range, 72, is very different to that standard deviation of 12. Good. Right. What's our average BMI for our participants? about 25.07. Good. So that kind of falls just on the verge of healthy weight to overweight, which is actually quite good because most of the data sets that I have done in the past, BMI is highly skewed to the overweight range. So this is actually quite a lighter group than you would normally see, potentially because they all have been plant-based for their entire life. Or not. That's just assuming, because this is descriptive statistics and not inferential, so we can't say anything is significant here. What about our Center for Epidemiological Studies of Depression scale? What's our average depression score across the data set? (14.28). Excellent. And by looking at the little label that we have above that, with a range between 0 and 60, with higher scores equaling greater depression and a cutoff of 16, what could we assume about our data, about our participants in our data set? Yeah, it is. They're all under the cutoff score. On average, our participants are under that cutoff score. This is also quite unusual to see, and already telling me something about my data set, particularly in comparison to other data that I have collected in the past, where mostly on average people are over that cutoff. So that's very interesting to start off with. The general population answer questions to give a non-depressed score on this instrument. Potentially, Matt, potentially, and that's something that we need to keep into consideration. However, we're still only looking at descriptive statistics, so this doesn't tell us if that is a significant finding. Right, our dietary screening tool, higher scores equal greater diet quality. Our average is about 65, so that's telling me average diet quality maybe. Social connectedness scale ranges between 20 and 120, with higher scores equaling a stronger sense of social connection. Our average is about 83, so that seems up there on the higher scale on social connection. And then our sleep quality scores range between 0 and 84, and we've got a 27, indicating greater sleep problems. So with a lower sleep quality score, that kind of suggests that we have a population who aren't having trouble with sleep, which is very interesting. So that gives us a snapshot. Again, you would put this into a participant characteristics table and you would report only the important information. So the averages, maybe the standard deviations, if there's anything interesting in there, and the range and minimum and maximum of age, usually we would report as well. So the participants range between 13 and 85 years, with a mean age of 39.57 and a standard deviation of 12.74. The average BMI was on the verge of healthy to overweight at 25.07, with a standard deviation of 5.45. And please see table 1, something like that. Good, good. Now, the rest of the data that we've asked for here, we'll start looking into our assumptions. The assumption of normality, we just want to see whether there are bar charts. Where are our histograms? Here we go. Okay. So these histograms, we just want to see whether they're on a normal curve. What do we think about age? Do we think age is a normal distribution or not? Yeah, Katerina, I agree. It looks normal to me as well. We've got a couple, we've got the 13, the 16-year-old here, and we've got the kind of older 75 to 85-year-olds here. But all in all, that's a pretty normal distribution. So we're pretty happy with age. What about BMI? Yeah, and this is this is what it is. Katarina says skewed and Miranda says normal. So the judgments on these normalities are always up to the researcher and the researcher's team. So always working together in a team and never making decisions in isolation is important. BMI is usually a lot more skewed than this. So we've actually got quite a healthy distribution here with only very few people on the tail here in the higher sections, which is very unusual. Usually it's highly skewed to this higher weight range. It looks opposite to that. So it's very interesting in this data set to compare that to what we normally see. But yeah, semi-normal, nothing to worry about. Now, the two variables that you are only worried about normality are your outcome and your predictor variable. So that tells us normality of age and body mass index. That's not to worry because they're not part of our research question. Our research question is focused on depression and diet quality. So these are the two variables we are most concerned about normality. So what do we think about depression? Skewed. Good. You are correct. It's skewed to the healthy range, though. If we remember that 16 is the cutoff score, our skew is down the healthy end. Now, this is what we want to see. If we see a normally distributed depression score, there is something very wrong with our data or something very wrong with our participants, because that means most participants would fall kind of in that depressive cutoff score area. So it is very common to see a depression scale data to look positively skewed like this. That's a problem for our data analysis because depression is always skewed. So we always have to do some form of transformation when we are dealing with this type of data. And that just means clicking a button to bootstrap the data or using a non-parametric test like Spearman's. So it's not a big deal if you see skewed data. It should be skewed. If this wasn't skewed, your participants would be having a very bad time with depression. What about dietary quality? It's our other variable that we're interested in seeing a normal distribution. What do we think about dietary quality? Skewed? Does everyone agree with that? It is a bit of a head scratcher, Miranda. I would consider it to be semi-normal, yeah. You've got your really healthy beans down here who are like kind of skewing it a little bit. But if we look at the majority, there is a pretty normal distribution of diet quality. So we don't really have too much of a problem with the assumption of normality. We were expecting to see a skewed depression scale before we came into the data set. And our dietary quality looks pretty normal. Social connectedness, again, that's looking okay. Sleep quality is a little bit skewed, but again, it's down the healthy range, so most people aren't having sleep problems. So that's how we interpret our descriptive statistics. The next thing that we do, we've already looked at our assumption of normality. So the next thing that we are going to do is we're going to look at our other assumptions. Now, who can remember what our assumption of independence, how we met that? How do we meet our assumption of independence?
Research design.
Yay, thanks, Matt. Yes, as long as we make sure that in our research design that no two participants do the intervention and the control, or have influenced their answers on the experiment, or in surveys haven't done the survey more than once, or haven't influenced their friends' answers on their surveys, your assumption of independence should be met. Now, we've also looked at the assumption of normality using our histograms. So the final assumption that we need to look at is linearity. Now, with linearity, all we have to do is go to graphs, and produce a scatter or a dot plot. Scatter plot We want a simple scatter with two variables. The first variable is depression, which I'll put on the X. Oh, am I going to put it on the right one? It doesn't really matter because they're both continuous variables. Put on the X-axis diet quality. I'll put on the Y, and we'll just see if there is a linear relationship between the outcome and the predictor variable. So there we have it. There's our scatter plot. Each dot on the scatter plot is one participant's score on depression and its relationship to their score on diet quality. So if you have a look down here at 0, so someone who has a score of 0 on depression here has a diet quality of about 45. So this dot here is one person. Whereas this person over here who has a depressive score of 40 has diet quality of 85. Now, how can we tell if there's a linear relationship between these dots? SPSS will tell us that. So if you double click on the graph, can everybody see that there? Add fit line at total. Yeah, good. Click the add fit line at total, close the box, close the other box. I lost them a bit, the variables. That's okay. Pop them back up. That puts a line directly onto our scatter plot. Now can we answer the question, can we put a straight line through those dots? Yep, great. We have met our assumption of linearity. So with our assumptions, yeah, go for it.
Sorry, Megan.
Yeah.
Before you put the line through there doesn't seem to be an apparent linear relationship. It really looks as though they're distributed quite randomly. Have you got any comment on why that line is where it is?
Yeah.
Looking at it, it appears that it could be, placed, basically anywhere.
That is a really good question, Daniel. And this is why we put the fit line on with SPSS, because to the untrained eye, it looks like a scattering of dots that have no relationship, right? When we apply the line, to me, this looks like, without the line on there, I can see the linear relationship. The dots seem to be trending from the top right to the bottom left in a downward pattern. A non-linear relationship. Yes, Daniel?
Yeah, no, sorry to interrupt. I can see it very subtly as well. Thank you.
No worries. A non-linear relationship would look like the dots would be in like a W shape or a U shape. That's what a non-linear relationship would look like.
Okay, thanks for explaining that point. I appreciate it.
No worries at all. The interesting thing, and when we get into regression in the next workshop, is that the scatter plot not only tells us the assumption of linearity, it also tells us a little bit about the relationship between diet and depression. And the R squared up the top there that the line produced also tells us about the strength of that relationship. So although you couldn't see the pattern, you were very correct about the strength of the relationship. So an R squared of 0.07 means that there's a very weak relationship between diet quality and depression in this data set. So you're kind of right. You were on the right track. Yeah. So linearity is literally that you just can put a straight line through your scatter plot. And the only time it's non-linear is when it's in a W or a U shape.
And Megan, the lower that R value, the stronger the relationship. Is that correct?
The closer to 1, the stronger the relationship. The further from 1 or the closer to 0, the weaker the relationship.
Okay, thank you. So opposite to P, basically.
Yeah. Also, if the relationship is positive, then as depression goes up, as diet quality goes up, depression goes up. But if our relationship is negative, as diet quality goes up, depression goes down. So remember that, because we're about to find out what the relationship is. What we've discovered so far are descriptive statistics that tell us what our data looks like, and our assumptions that kind of also tell us whether or not we can complete an analysis. What these things don't tell us is whether there is a significant relationship or a significant difference between the variables. And that's what our inferential statistics will tell us. So that's what we'll do now. We'll do the easiest inferential test of all time, correlation. In correlation, we are going to answer that research question. Is there a relationship between diet quality and depressive symptoms in those who follow a plant-based diet? And that's all we're asking. Is this relationship significant? So to do so, we would go to, can everyone see SPSS? Oh. Analyze, correlate. Correlate just means relationship. Bivariate, which means we have 2 variables. The variables of interest are Center for Epidemiologic Studies of Depression Scale. If you right-click here and display the variable names, it will actually give you your variable names instead of the full description, which might make it easier for you. So we put depression in, and the other variable that we are interested in the relationship between is diet quality. That will answer our research question. But at the same time, we can also have a look at the relationship between depression and our other variables of interest, like social connection, sleep quality, and physical activity if we wanted to. So you don't have to just do them one at a time. You can have a look at the relationships between depression and all of the variables at once. Now, here we have our different correlation analyses. Pearson is the relationship when all of our assumptions are met. And then Spearman's is if we have problems with our assumptions. So we might be actually better off running a Spearman's this time because our depression variable is a little non-normal. But both of these will give very similar results. Spearman's is just adjusting for that non-normality. We could do Pearson's and Spearman's at the same time as well, so you can have a look or compare. And that's all good. Or if we want to, we could bootstrap to adjust for that problem with normality. So there's 2 different options that you can do because we have that non-normal variable. So we click OK. I will share the outcome.
Do you just do one or the other? Like you don't bootstrap, you'll do like Pearman's and Spearman's, or would you just do bootstrap? Like
you could do both. You could bootstrap and do Pearson's and Spearman's and just compare whether there's big deviations between all of the results that you get. Keeping in mind that the ones that say non-parametric correlations are your Spearman's, so that one's adjusted for the problem with normality. And then the ones that just say correlations are your unadjusted ones. So let's just have a look at the relationship between depression and diet quality and see if there's a big deviation between the Spearman's and the Pearson's relationships. So what we're interested in is, first of all, the relationship between depression and diet quality. So we go the depression row and all the way over to diet quality, which is this row here. What is our correlation between diet quality and depressive symptoms? Statistically. Daniel wants me to explain bootstrapping. Can I send you a video on bootstrapping? It's a bit complex, and the video that I show my undergrad students is the most simple way of explaining it. So Alison, if you can remind me with the slides to provide the bootstrapping video as well.
Yep, yeah, sure, will do.
I don't want to confuse everyone. So our relationship between depression and diet quality is -0.28. Remembering we are rounding to. So what does that mean? So a negative relationship means that as diet quality goes up, depression goes down. Now that's what we wanted to see, because that would be what my directional hypothesis would be. So that's good. So firstly, we know that in this data set, the relationship between diet quality, as diet quality goes up, so higher diet quality, lower depressive symptoms. So that's good. The first thing that we want to know is, that's nice to know about the relationship, but is that significant? So if we have a look at the significance, what is our significant value? Massim's saying yes, yes. How do we know that's significant? It's been set at the 0.05 level. Very good, Matt. Yes. It's less than 0.05, so we have a significant relationship. So far we know we have a significant relationship between diet quality and depression. We also know that as diet quality goes up, depression goes down because we have a negative relationship. And then we can tell the strength of the relationship from the actual statistic, because a correlational statistic is also an effect size. So 0.28 would be a medium effect. So in correlation, anything greater than 0.5 is a strong effect. Anything around 0.3 is a medium effect, and kind of under 0.2 is considered a weak or no relationship. So we've kind of got like a moderate relationship there. Even though when we scanned the scatter plot, we thought that it might be a weak relationship, it's actually moderate. So this is why inferential statistics or inferential testing is very important. We can also have a look at depression and the other variables. So social connection, and this is one of the most interesting things about my research to date, is that we always see this relationship between depression and social connection. Can anyone tell me what direction the relationship is between depression and social connection? Matt, 0.65, yes, strong. So it is a strong relationship, and it's negative, which means that as social connection goes up, depression goes down, and it's a very, very strong relationship. And we see this time after time after time after time. Sleep quality is the same. Sleep quality is 0.72, which is a strong relationship. It's significant, and we know that higher scores indicate greater sleep problems. So this relationship is positive. So as sleep problems go up, depression goes up. Good. Any questions about our correlations or our relationships before we move on? I know we've only got another 10 minutes to do group differences, which is our t-test. This is great. And don't worry, in the next module, the workshop that we're doing on regression, we start regression with correlations because it's the little brother of regression, and you have to do a correlation before you can do regression. So we'll go back over this in the next workshop. Right, so finally, we're going to look at group differences. The easiest way to look at group differences is by doing a t-test. Now, keep in mind that when you're doing t-tests will only measure when you have two groups. Any more than two groups, you need to do ANOVA, and we will do that in a future workshop on advanced statistics. So keeping in mind the t-tests are only for two groups. So let's have a look. Let's analyze, compare means and proportions. So a t-test in its purest definition is comparing the averages of two groups. Pretty easy. So we want to do, so if we're looking at our research question, do vegans or vegetarians have higher depressive symptoms? Who can tell me whether the participants in the two groups are the same or different participants? So if our two groups are vegans and vegetarians, do we have the same participants in the two groups, or do we have different participants in the two groups? Different, excellent. Yes, so we have classified all the vegans as people who consume no animal products, and we've categorized all the vegetarians by self-report as those who don't eat meat but may consume other animal products. So let's analyze, compare means, and we want to do an independent samples t-test because the two groups are independent of each other. In the grouping variable box here, we want to find our variable vegans and vegetarians, and we want to define the two groups. We've got vegans as 1 and vegetarians as 2. So we've got that in our grouping variable. And then we want to have a look at depressive symptoms between the two groups. Now we can just do one t-test and look at that, but we could also do multiple t-tests looking at our other variables like social connection and things as well if we wanted to. But for simplicity's sake today, we will just do the CESD total, or the depressive symptoms total. In this situation, I believe we should bootstrap because our assumption of normality on our outcome variable is not met. So we will bootstrap, we will perform bootstrapping, keeping in mind you're going to watch the video and understand bootstrapping a little bit more. Continue. Okay. Then I'm going to stop share and I'm going to share my outcome or my output. Here we have it, our t-test. With 5 minutes to go, we're right on time. So the first box for a t-test will tell us the differences between our two groups and our bootstrap confidence intervals. Now, we won't get into that too much right now, but to interpret a t-test, we have that final assumption of homoscedasticity to deal with. So before we can do a t-test, we need to ensure that the vegan and the vegetarian groups have similar variances. To do this, SPSS automatically conducts a Levene's test to test for the equality of the variances. And this is our assumption of homoscedasticity. Who can tell me whether or not our assumption of homoscedasticity is significant or not? Looking at this variable here, the F statistic underneath the Levene's test, is it significant or not significant? Matt, I'm going to come back to your question in a second. Not significant. Okay. So this is a good thing because it's greater than 0.05. We don't want our assumption to be significant. Otherwise, we will have a significant deviation of our assumption. So we want it to be non-significant, which it is. If we read from the top line and our Levine's test is non-significant, then we will move forward in interpreting our t-test with equal variances assumed. So which row of t-test would we read? The top row or the bottom row? Are you sure? No. Right. So we're reading from the top row because we have a non-significant value for homoscedasticity, which means there is no significant deviation of our assumption. So our assumption is met. So equal variance is assumed. Our t value is 1.46. What is, because we've bootstrapped, it doesn't give us a p-value. So that top value, 1.45, is our t-test. And then for significance, what is our, what's our significance value here? Remembering we did a two-tailed test, so our two-tailed p-value is? Can anyone tell me what our p-value is right there? Not significant. Good. So what does that say about our research question? About, what was our research question? Is there a difference between depressive symptoms of vegans and vegetarians? No, that's right. So we have a non-significant t-test. So there is no difference between the depressive symptoms of vegans and vegetarians. Good. If your t-test was significant, you would then go on to report what the difference in the mean is. There was a 1.63 difference between vegan and vegetarian depressive symptoms, but because there is not, you would stop and just report there is no difference in vegan and vegetarian depressive symptoms. Very good. Now, Matt had a question up here. Aren't they the same because they're from the same data set demographically? They are from the same data set, but all of the vegans are being measured against all the vegetarians. So no one participant can be in both the vegan and the vegetarian group when we categorize them in the way that we did. If they did, if the participants were the same, then we would do a paired samples t-test. No worries. Are there any other questions before we move on? No? Okay. So next time we will move on to regressions. And as I said before, we will cover correlations again because correlations are the first step in any regression. You cannot do a regression without a significant correlation between two variables. So correlations are always your first step in regression. So we will just be building on what we learned today, basically. And then we will also move on into understanding a little bit more about differences between more than two groups. So we'll be looking at ANOVAs. So if we have 3 groups or more. If you have any questions or would like any further clarity or clarification about any of the concepts that we talked about today, feel free to email me at my Bond email address. If you're interested in any of my research, including my diet and depression research, feel free to check out my website or any of my socials. I like doing lots of fun foodie pictures, so love to have you on there. The recordings are available at the SCPA YouTube and also on my website. And I'm looking forward to seeing everyone on the 2nd of May for the more advanced workshop.
Excellent. Thanks, everyone. Thank you, Megan.
Thank you, Alison.